should I start the introduction or?
Yeah, go ahead, Akram. I think it's probably good, unless there's anyone anyone you see obviously not here. We're good. Yeah.
Okay. So it's my pleasure to introduce Tye Lidman from North Carolina State University. Yeah, I did write this down. He's going to tell us about Heegaard Floer homology and branch level covers. Thanks, Tye.
Great. Thanks for the invitation. I love getting to see everybody, so it's great to see so many familiar faces. I will try to monitor the chat, but I don't know if that doesn't work. Maybe feel free to unmute yourself or ask a question, or maybe Akram or someone else. If your chat doesn't get answered, just feel free to interrupt me. And everything that I'm going to say is joint with Kristen Hendricks and Robert Lipschitz. So let me start with a little bit of background. Which is maybe familiar to a lot of you, but I also know that there's a sort of lot of symplectic topologists as well that come to this seminar. So I wanted to try to give kind of a broad overview of what we're going to be doing. And I'm going to start with a question that has kind of nothing to do with three manifolds or Floer homology or anything at the start. I'm going to give some kind of algebraic construction. So let's suppose that G is some non-trivial group. And I'll say G is left orderable. Basically, if there exists a strict left invariant order on the group G, and so really what I mean by this is basically there's just some order such that if G is less than H, then I can multiply on the left by any element and I'd get, say, KG is less than KH. For all, I should quantify, for all G, H, and K in my group G. So it's just a left orderable group is just a group with some nice sort of left invariant order on it. And you already know lots of examples of this, but one of the simplest examples is just the group Z with the usual order on it. So if A is less than B, then I can add C to both sides and the inequality will still hold. So this is sort of an interesting question, which is which groups have this kind of orderable structure, and not all of them have this kind of orderable structure. For instance, let's say I'll give a non-example. So if G has torsion, then G is not left orderable. And in fact, we can give a quick proof of this. And the way that this proof goes is, suppose there exists some left order on the group G, and let's pick a torsion element. So let's let G to the n be the identity. And now, well, up to maybe taking the inverse of G, G is some positive element. It's bigger than 1. And then we can multiply on the left by G, and we'd see that G is then less than G squared. G squared multiplying on the left would give us G squared is less than G cubed, and so on until we get to G to the n, which is 1. And so this violates our strict total order. 1 can't be less than 1. Okay, so some groups have this left order structure, some don't. And we could ask a few questions, which is, 1, who cares? And 2, what kind of algebraic information can we actually extract out of this? And kind of maybe unrelated, I'll just point out that there's sort of a dynamical characterization of this, which we won't really have time to get into. But I want to just point this out as sort of a different viewpoint on this notion of left orderability. And the dynamical characterization is that if G is a countable group, then left orderability is the same thing as embedding inside of the orientation preserving homeomorphisms of the real line. So basically being left orderable kind of means you have this sort of like nice action on R, basically. It's nice sort of faithful action. Okay. So that's sort of the whole general algebraic theory of left orderable groups. It's been around for many decades, and there's some relations to studying algebraic problems about group rings and the word problem and so on. But I'm sort of going to skip all of the rich history of this theory and just jump into why we care about it from a topological perspective. And it does show up in a lot of different ways in topology. But in particular, one thing I want to talk about is that this behaves in a very special way for three manifold groups. So I'll just say for the fundamental groups of three manifolds. And the way that this manifests in particular is through the following theorem of Boyer, Rolfson, and Beast. And let's say we have a three manifold Y, and let's suppose that it'll be closed, orientable, although this is not really necessary, but just to make the statement simple, we'll assume it's closed, orientable, and prime. And the statement is that if there exists some non-trivial homomorphism to some group which is left orderable, then the fundamental group of the three manifold itself is left orderable. So basically, if you have sort of a representation to a left orderable group, then you are left orderable. And this kind of sort of like residual property of left orderability is really special to three manifolds. And I'll illustrate that with an example. We could look at Z plus Z mod 2. And this surjects the group Z. Now Z is left orderable. We said we have just our usual order on it. And Z plus Z mod 2 is not left orderable because there's torsion. And so in particular, this tells us that Z plus Z mod 2 can't be the fundamental group of a three manifold. So it's kind of interesting. There's something peculiar going on. And I think maybe over the past 20 years or so, there's been a lot of interest in what does this left orderability say about three manifolds? There's some relation, there's something special about it. And the proof of this theorem actually uses some deep results in three manifold topology. So for instance, it uses the Scott compact core theorem. So it's something that sort of sees something intrinsic about the topology of three manifolds. Okay. And I want to point out sort of one special case of this. Special case. Which is if there exists a non-zero degree map let's say from one three manifold Y3 to another three manifold, sorry, let me switch the order. Let's say from Z, some three manifold, to Y, some other three manifold. Again, let's say closed, orientable, and prime. And pi1 of Y is left orderable. Well, then we have a homomorphism from the fundamental group of Z to the fundamental group of Y. And if it's a non-zero degree map, in other words, if it induces a non-trivial map on H3, then actually that map has to be non-zero on pi1. And so actually we get that pi1 of z is left orderable as well. And so this left orderability gives you, for instance, it gives you an obstruction to non-zero degree maps between spaces. And if you want a very special case, is that if z covers y, then pi1 of z is a subgroup of pi1 of y. And so we could actually then just take our order on pi1 of y and restrict it to get an order on pi1 of z. Okay, so any questions about any of these ideas before we sort of get more into the three manifold world?
One question, do you know what got Bayer and Rolfson and Weiss to look at this property for three manifold groups in the first place?
Yeah, where were they coming from? I mean, so Dale Rolfson, I think, had also been thinking about sort of orderability with respect to braid groups. So for instance, the braid groups have some interesting order structures. So there was already some kind of like some things going on there. And I think kind of what I'm about to say is maybe going to build this connection a little bit, but there was also some connections with foliations that were arising right around the same time, which is also what I'm gonna mention. I don't know if somebody else may know the history of exactly what they were thinking right when this came out. They should feel free to interject.
When did it come out?
Oh, early 2000s, I think. I think it was like, I mean, I think it was just a little bit before people were thinking about how Floer homology related to foliations and things like this. But I could be wrong.
Like the work on orderability of the braid group, that was earlier, right?
That's earlier, and I think Dale had been thinking about this. And so probably was trying to go from surface type information to three manifolds, but I could be wrong. Okay. Good. Okay, so right, so there's some questions as to what is left orderability seeing about the three manifold, and I'm going to state one approach to this, answering this question, which is called the L-space conjecture. And it's in its sort of original form, this is due to Boyer, Gordon, and Watson, which this comes some number of years after this Boyer, Rolfson, and Wiest result. And I'm going to give some sort of like overkill. I'm going to give maybe an even more strong version of the L-space conjecture than what you may have seen before, just for fun. I don't know, it's no fun to put out weak conjectures. So I'm going to put out an extra strong conjecture, which I think is maybe might spark some more interest based on some of the interests of people at UGA. So let's suppose we have a prime three manifold, again, closed, orientable. And I'm going to claim that the following things are all equivalent. So the first is that pi1 is left orderable. The second is that y admits a co-orientable taut foliation. And we won't really talk about that today, so I won't spend much time on it. But basically it means that your three manifold can be foliated by surfaces such that there's a loop that runs transverse to all those surfaces. And what we are interested in is that this is also conjecturally equivalent to the statement Y is not an L space And then I'll add one more thing, which is that Y with either orientation admits a symplectic filling with B2 plus positive. So I'm not going to talk about the second or the fourth conditions in this. So if, I'd be happy to talk about it afterwards if people want to hear more about this. But what we're really going to focus on today is relating the first condition and the third condition. And in particular, I'll tell you what this third condition means in a second. But what one should have in mind for this is that left orderability, this is some algebraic condition, something about the fundamental group. And the coorientable top foliation, maybe you can think of this as some kind of topological condition. It's something about surfaces in your manifolds. The L space condition, this is some sort of analytic property of your three manifold. And this being an L space can be described in various ways, but in one way it can be described as something about solutions to some kind of PDE on your three manifold. And then I don't know what this symplectic filling with B2 plus greater than 0 kind of thing can be. This is some sort of 4D, I don't know, TQFT information. So it's something about the kinds of four manifolds that your three manifold bounds. And this L space conjecture, this sort of new made up version that I'm giving you here, kind of just telling you that all these things should be related. Okay. So in order to make any sense of this, we know what left orderability is. I should tell you what an L space is. So I'm just going to say sort of just a couple words about what an L space is. And well, it's basically, so an L space, so I'll define this in a way that may not be helpful for you to start. So I'll say an L space is a rational homology three sphere such that I'll say the dimension of the Heegaard Floer homology is given by the order of the first homology. So here HF hat just means Heegaard Floer homology. So if you haven't seen this before, then I should tell you a little bit about what Heegaard Floer homology is. So that's the next part is what is Heegaard Floer homology? And I know there's quite some number of experts in the room about this, but I still wanted to just give some very, very quick overview before we get into it, because we will actually, I don't know, maybe it's not so common anymore in Heegaard Floer homology talks to see Heegaard diagrams coming into the picture, but we actually need them in this talk. And we even need something about Lagrangian Floer homology. So I do want to say a little bit. I don't want to black box it as much as I normally might. Okay, so how does it go? So I'll just describe the steps to the construction. So first, what we're going to do is we choose a Heegaard diagram for our three manifold. And so what is a Heegaard diagram? It's a choice of Heegaard splitting, basically. So we pick our three manifold, we divide it up into two handle bodies. So for instance, we think of S3 as being decomposed into two solid tori. And then we kind of there's some way that we can diagram this on the surface that's splitting up our three manifold. So I'll just draw an example here. I have a genus 2 surface. And I'll put some curves on here, two curves that specify one of the handle bodies and two curves that specify the other handle body. So you should think of these curves as giving you the compressing disks for the handle bodies. And we're going to actually put a base point down, because why not? So we have a base point Z also. So, but this is sort of what a traditional Heegaard diagram for your 3-manifold might look like. And then from this data, we're going to build our invariants. So given our Heegaard diagram, let's say sigma G, and then this collection of compressing disks or boundaries of compressing disks alpha and beta, and this base point Z, we consider 2 tori. I'm going to call one T alpha. It's just the product of all of the alpha curves. And another one T beta, which is the product of all the beta curves. And I could think of these as living in the, say, the G-fold product of the surface, but I actually put them inside of the G-fold symmetric product of the surface. And just recall the G-fold symmetric product, I just take G copies of the surface and I mod out by the symmetric group. Okay, so now I have these, and it turns out there's a nice symplectic structure on the symmetric product, and the T alpha and T beta, these tori, are Lagrangians. These are Lagrangian submanifolds of this strange symmetric product manifold. Okay, so I've gone from the surface information of the 3-manifold and I've turned it into some kind of high-dimensional symplectic topology situation. And then I just define the Floer homology of Y to be the Lagrangian Floer homology of T alpha and T beta. And if you haven't seen Lagrangian Floer homology before, basically it's just roughly, it's some abelian group, or for us, some vector space that roughly counts intersections of these 2 tori. And it packages that information together with how they sit inside of this ambient symplectic manifold. Well, it just sort of packages that information into a vector space. And I'll just do one quick example. And in this one quick example, I'll do the Heegaard splitting. I'll do a genus 1 Heegaard diagram for Ln1, or let's do L31. Oh, well, actually, let's just say this is Ln1. Why not? Here's a picture of Ln1. And you see these n intersection points here that I'm drawing in black. And each of those gives me a generator of this Lagrangian Floer chain complex that I use to build the homology. It turns out the differential will be identically 0 because these are all supported in the same Z-mod 2 grading. And this will be n copies of whatever our base field is, our ground field. And that's exactly equal to the order of H1 of a lens space. So Ln1 for any n, in particular including S3, is an L space. And we can compare this to our original conjecture. I'll remind you that being an L space is conjecturally supposed to be equivalent to not having left orderable fundamental group. And so we can compare to pi1 of Ln1 being Z mod n, which is torsion. And so not left orderable. So this sort of lines up, this simple family of elliptic manifolds, these lens spaces, this lines up with our conjecture that not being an L space, so having this sort of particularly special form for your Heegaard Floer homology is equivalent to having non-left orderable fundamental group. Okay, and maybe I'll pause again if anyone has any questions about this setup. Okay, I think this is familiar to a lot of you. So the philosophy that I've taken for the past several years, and I think I've described this philosophy at UGA in a talk back in 2015, is can we kind of translate between these different areas? So can I use, say, something I know about left orderability to predict something about Floer homology or vice versa, and try to get.
Tye, can I answer a question? I'm sorry, I meant to.
Yes, please.
Just to put everything in context. So, are there maybe lots of examples of L spaces, maybe that don't have torsion in pi1? You know, things that aren't for which there's not an obvious reason that it's not left orderable.
That's a great question. Yeah. So there's some. We could look at some more interesting examples, and maybe I should add in some more interesting examples. So, so for instance, you could look at something like, okay, let me give this example of Boileau and let me attribute this to Boyer and Clay and Hanselman, Rasmussen and Watson. Which says that, well, so if Y is let's say is a graph manifold, or if you want, just think a ciphered fibered manifold, then this conjecture holds. Well, what does conjecture mean? Then pi1 is left orderable if and only if Y is not an L space. So if you want some more interesting examples, you could say, for instance, take surgery on any torus knot in the three sphere. So do a Dane surgery on the trefoil, and if you do any large Dane surgery on the right-handed trefoil, you'll produce an L space. But most of those will have, say, infinite torsion-free fundamental group. Yeah, if you want. Let's see, are there other good examples? Is that helpful, Dave?
Absolutely, thank you.
Great. Okay, good. Lots of, I like questions. Any other questions?
Like a simple like what's the simplest possible counterexample?
Oh, that's a good question. What's the simplest possible counterexample? I think it's Dane surgeries on knots in S3 in general, this is not known. Same thing for cyclic branched covers of knots, maybe even twofold branched covers of lots of knots. So there's, I don't know if there's a good particular knot and surgery that's particularly accessible. I think for a while it was unknown if this was equivalent for all surgeries on the figure 8 knot, for instance. That may have been sorted out recently, but I'm not sure. But like you could write down a pretty simple knot and you could start doing Dane surgeries, and it's easy to figure out whether or not it's an L space, but the left orderability is quite tough. There just aren't good, left orderability lacks a lot of techniques that sort of Floer homology is good at. So we don't know anything about how does left orderability behave under cobordisms. And even Dane surgery is quite hard. There's some results along those lines, but it's quite hard. But that's a good question. Okay, any other questions? Okay, so as I was just saying that, things like Dane surgery and cobordisms, things that Floer homology is well behaved under, there's not so much for left orderability. There are things that left orderability behaves well under, like for instance, we saw looking at subgroups or looking at covers or non-zero degree maps. And so that suggests something for Floer homology. And so I'll just kind of translate the original thing I said about non-zero degree maps into Floer homology. And in particular, I'll say, the conjecture is that if, let's say f from z to y is a degree non-zero map, then y not an L space implies z is not an L space. And this, maybe make this.
Can I go back and ask another question?
Yeah, of course.
What about like not groups being left orderable? Is that anything interesting or known about that?
That is an interesting question, but what happens? So for a not group, so let me back up. Okay, that's some time ago. Okay, right. So this Boyer, Rolfson, Wiest, you really don't need closed. I don't even know why I wrote closed. It works for compact orientable prime manifolds, and in fact, any compact P2 irreducible three manifold. So in particular, if you take a not group, you can abelianize to Z. And so then that shows that all not groups are left orderable. But then there's the question of bi-orderable, when you have a bi-invariant. When you have a bi-invariant order, and that there's a whole bunch of interesting work done there. Some knots have bi-orderable knot groups, some don't. How does that relate to left orderability? Some things like this. So I think Jonathan Johnson is maybe one of the people that sort of has the most recent results on this, but it's still pretty unexplored. We don't know so much about it. Or how does bi-orderability of the knot exterior tell you about left orderability of surgeries or branched covers? Like all this kind of stuff is kind of pretty open. Good. Okay, so let me come back to this conjecture. Sort of something that I spoke about here in, let's say, 2015 is some joint work with Ciprian Manolescu, which says that this is true sometimes, and I'll kind of just give a very special example of this, which is just, I'll just say if Z is a two-sheeted cover, if Z is a two-sheeted cover of Y, and Y is not an L space, then Z is an L space. Oh, sorry, then Z is not an L space also. And there's some more general statement here, but this is sort of the simplest version. So for some covers, this is nicely understood. But the proof doesn't use any symplectic topology. So the proof passes through gauge theory. And maybe I'll point out one other example for which this is known. So there's a theorem of Hanselman, Rasmussen, and Watson, which sort of makes use of some mirror symmetry in the punctured torus to prove the following. So let's say I have M1 and M2, two three manifolds with torus boundary, and I glue them together to get Z. And I just take one of these three manifolds that's complicated, and I replace it by just a solid torus and keep the other part fixed. So F is sort of pinched to a solid torus. And in that case, again, this conjecture is true. So there are some known examples where you can get these kinds of results about this behavior under non-L space, or sort of behavior of non-L space under non-zero degree maps. And it's kind of peculiar. And in fact, these come from actually sort of stronger results where one proves a rank inequality between the Floer homology groups, not just whether or not one is an L space, you actually obtain a rank inequality. Okay. So what I want to talk about today is just some kind of variant on all of these pictures, which is that something similar works for branch double covers. So I'll state this theorem with, again, this is joint work with Kristen Hendricks and Robert Lipschitz, which says that, let's say we have L, which is a null homologous link, in some three-manifold Y. And let's suppose that the branch double cover of YL is a rational homology sphere. So that, well, sorry, let me phrase this better, sorry. Just say that if Y is not a null space, then the branch double cover of Y branched over L is not a null space. So again, this sort of just general property of what we expect for these kinds of covers. And in particular, we have a statement like, there's a more general rank inequality. So I'll say it probably like this: if sigma of YL is a rational homology sphere, then you also get a rank inequality that the dimension of HF hat of sigma YL is at least the dimension of HF hat of Y. And there's almost even a spectral sequence, but not exactly a spectral sequence. Okay. And I won't go into it today, but I'll say a similar result holds for sutured Floer homology. And I'd be happy to clarify that a little, what that means after the talk, if anyone's interested. But basically, if you have a link in a sutured manifold, you can take a branched cover and get a new sutured manifold, and you can relate the sutured Floer homologies. Okay, are there any questions about the statement?
When you say that there's almost a spectral sequence, is it that you actually do set up a spectral sequence? It just doesn't go directly from the things that you've written down. Like there's some other tensor factor or something.
That's exactly right. So, or
is it a completely different proof from what I would expect?
It's probably what you would expect, which is that it's some kind of localization spectral sequence. And so you would, what you're going to actually have is something like HF hat of sigma of YL tensored with some Laurent polynomial ring, and HF hat of Y tensored with some Laurent polynomial ring, and you have a spectral sequence between those two things. That's right.
Okay, cool. Thanks.
Great. Okay, so maybe for the last 10 minutes, I'll try to say something about the proof. And my philosophy on doing math is just like try to find someone else who did a lot of work and then just try to use their work and don't actually do too much work on your own. So that's the setup here. And let me kind of just describe the topological setup for sort of why one would even kind of relate these things or think they'd be related. And now maybe for simplicity, let's say L is a knot. If it's a link, you basically just work with some notifications in some connected sums with S2 times S1, but it's just some technical point. So we'll say that L is a knot, and we have that sigma of Y, sigma 2 of YL to Y is some branch double cover. And so what we'll do is we'll build so we pick a doubly pointed Heegaard diagram for Y and L. So that's just a diagram, a Heegaard diagram for the three manifold that knows about that somehow knows about this knot L. So we basically take the original diagram that we had and we have an extra base point in it. This is a Heegaard diagram for the unknot, so it's not particularly interesting, but given any link you can, or any knot, you can represent it by a Heegaard diagram where you put 2 base points down. So it's just some sort of combinatorial representation of this knot. So that's the first step. The second step is that we just, so maybe we'll give this a name, like sigma G alpha, oops. Let's say sigma G alpha beta ZW. And then we just take the branch double cover. So we branch double cover just all of this data. And so what that might look like would be this. And it's a branch double cover. So there's a deck transformation here, a Zmod 2 action. And you can kind of see it in this particular example, which is just, I skewer it and I rotate it by 180 degrees. And that sort of gives me exactly, when I quotient it, that exactly gives me the data below. So this is like sigma 2G tilde, alpha tilde, beta tilde, Z tilde, W tilde. And conveniently, this gives a Heegaard diagram for the branch double cover together with the lift of this curve. And so now we can just try to compare the Lagrangian Floer homologies of the associated Lagrangians. And how could we do that? Well, the key observation is, well, we could look at how this involution actually acts on the symmetric product. And the fixed set is going to be things of the form x1, tau of x1, x2, tau of x2, and so on. So recall an element of the symmetric product should be an unordered tuple, or sorry, an unordered set. And so the ones that will be invariant are things like their G points and then their G mirrors under the covering involution. So I should call this covering involution tau. So that's the fixed set. And this is identified with, so this is sort of naturally isomorphic to the original surface sigma G we started with. And if you also look, tau exchanges or tau acts on the Lagrangian tori as well, and the fixed sets, the fixed sets will correspond to the data for the original 3 manifold. So we'll get sim G of sigma G minus Z, T alpha, T beta. So it's not these on the nose as sets, but they're sort of diffeomorphic to these, or symplectomorphic to these with some suitable choices. So now basically the name of the game is how do you compare the Lagrangian Floer homology of some Lagrangians to the Lagrangian Floer homology of the fixed point set. So basically what we want to do is we want to compare so I'll just say it this way, we want to compare something like HF, the Lagrangian Floer homology of M and 2 Lagrangians inside of that M with the Lagrangian Floer homology of the fixed sets inside of the fixed set symplectic manifold. And you can check that this tau acts symplectically and that the resulting fixed point sets are sort of nice and Lagrangian still, that sort of all the symplectic structure is being preserved. And so there's precisely a theorem that allows us to do this. So we're going to use the following theorem of Large, which is kind of a generalization of the Seidel-Smith localization theorem, if you've seen this. And it's basically under certain technical hypotheses, there is a rank inequality between the Lagrangian Floer homology of the Lagrangians in the big space and the Lagrangian Floer homology of the sort of fixed point sets. So I'll say, I'll put it this way. I'll say if M, L1, L2 are exact and convex at infinity. So that's the first thing. And I'm going to add an extra condition. So this is some sort of technical hypothesis, which it's the symmetric product, punctured symmetric product satisfies. But I'm going to add a slightly weirder one, which is that there exists a stable isomorphism of bundles between the tangent bundle to the fixed point set and same thing with the Lagrangians. Oops. So there exists a stable isomorphism between this bundle and the normal bundle. Then we get a nice rank inequality. And so that's basically what we're interested in, right? We're interested in some relationship between the Floer homology of the branch double cover and the Floer homology of the original three manifold. And so all we need to know is that there exists a stable isomorphism. So in my last minute, I'll just mention first the theorem of Large, is that there exists this stable sort of tangent normal isomorphism for very similar involution. So for the same picture as, except when we remove both of the base points. And so that sort of gives you actually some rank inequality between the not Floer homology and the branch double cover and the not Floer homology, the not downstairs. And then just the main sort of technical theorem that I won't have any time to discuss because I'm out of time here is that, well, you can extend this to the relevant symmetric product, the one that we're interested in for computing Heegaard Floer homology, and not just not Floer homology. And we get, I'll just remind you, we get this rank inequality, the dimension of HF hat of sigma of y. L is at least the dimension of HF hat of y. And if you want to get the statement about L spaces, then one just has to be a little bit careful with the spin C structures. But basically, this is the inequality that guarantees the result. Once you do this sort of kind of sort of symplectic topology / algebraic topology bundle isomorphism. So I think I'm out of time, so I won't be able to say anything else about the proofs. So maybe I'll stop there.
Thanks, Tye. Any questions?
So how crucial is it that this is a double branch cover?
Good question. So Gordon, do you mean like why can't we do like a threefold branch cover or something?
Right. So where does it break down?
It breaks down in a stupid way, which is that it's a coefficients thing. So if you want to do sort of like Smith theory with Z mod 3, you need Z mod 3 coefficients. And so then you'd need to just do like all of this kind of then you can't work with Z mod 2 coefficients anymore. So then you need to orient all your moduli spaces carefully and things like this. And somehow, I think maybe in principle one can do it, but I don't know if in practice anyone's really been able to do any of these kinds of.
So where do you do Smith theory? Oh, you mean just comparing the homology for the fixed point set?
That's right. So that's where the Smith, it's sort of basically it's a Lagrangian, or it's like a Floer homology version of the usual Smith inequalities. And so you can, well, okay, somewhere you need to count moduli spaces and or orient moduli spaces if you want to do things over, say, Z mod P. And I think just like building these things it's a little bit hard. And also maybe I'll add one more thing, which is like, so somehow you should think of this as some kind of like, equivariant. This is some kind of like equivariant Floer homology, some kind of like Z mod 2 equivariant Floer homology should be showing up. And so that's like something modeled on RP infinity. You'd need some kind of like model for LP infinity, or sort of infinite dimensional lens spaces. Again, I don't know if anything is like abstractly that hard, but to actually do all the orientations and of the moduli spaces and things, I don't know. I mean, I think that, so there's another approach. I should add one more thing. Sorry, I'm just rambling, but there's a third approach, which, it's not nice of me to leave this out. I should also point out that this also kind of builds on some similar work of Hendricks, Lipschitz, and Sharkar, where they also have a different take on equivariant Lagrangian Floer homology, and I believe they can do other group actions, not just Z mod 2, but somehow Tim Large's thing, which is sort of the most general one, where you can use this sort of stable isomorphism instead of a stable trivialization of the tangent bundle, stable trivialization of the normal bundle. He has sort of like a lot of extra work that one would really need to do over Z. Like there's some sort of thing similar to the Cronenberg-Mrivka construction of monopole Floer homology, where you do some kind of blow up near the fixed point set so the action becomes free. And somehow there's just a lot involved in what he's doing. And I think it'd be a lot of work to make it work over Z.
It's just a general comment that all these this equivariant DP equivariant stuff was actually done in a paper of at least some, maybe part of the framework was done in Igor Shalukin and Jingyu Zhao's paper. That they kind of do it in for different equivariants in Floer theory, that they consider this equivariance in loop space, but I think they prove some sort of sigma p Smith inequality over there.
Oh, I didn't know this. Okay, I should look into this.
This is for fixed point Floer homology of symplectic morphisms.
Right.
But like the model of LP infinity and stuff is certainly in there.
Yeah, some basic things are there ready.
Okay, great. So Gordon, I guess it sounds like we should do it. We should all do it. That sounds great.
Other questions? Okay, so if there's no other questions, let's thank Tye again.
I'm going to
And
stop the recording, and
Thanks.
then you can ask all your other questions.
Sounds good.